Alright, so in this video we're going to continue on with electromagnetic induction, and we're going to start by talking about something called Lenz's law. And basically the way I think of this law is essentially what it boils down to is nature hates a change in flux. That's what it basically boils down to. Anytime you change flux or flux is changed through a surface, that surface reacts in a way to try and cancel that change out. If you add flux, what it tries to do is it tries to create an electrical current that creates a flux pointed in the other way that'll cancel it out. If you take flux away, it tries to create a current in such a way that it creates a magnetic field that it adds back what you took away. All right, so it tries to undo what changes are done to it. All right, you add flux, it tries to take it away. And so how can we change flux? So this is our Lenz's law. When flux is changed, nature tries to undo that change. It tries to counteract that change. It tries to counteract that change, but it usually can't fully do it. It can usually only partially do it because there's resistance to electricity flowing and everything like that, with the exception being in superconductors, which we can maybe talk about some other time. But how do we change this flux? Let's look at how to change flux, and this may help you kind of see how this works. Okay, so how do we change flux? And the first way is to move a loop move a magnet near a loop. So let's say we had a coil of wires. Here's our coil of wires, and what we can do is put a magnet over here by it, right? Over here by it, or even inside it. That could be north, that could be south. And then what we're going to do is spin that magnet. We can spin it and rotate it, and you would think about it here, the magnetic field is coming in this way, and then as it turns and the north faces here, then the flux is going to be pointed the other way, and so one causes flux this way. When the north switches, it causes flux in the opposite direction. I don't know if you can see what I'm drawing there very well. So when the south is facing, you're getting flux pointed to the left. When the north is over by it, you're getting flux pointed to the right. And that changes the flux through this loop, so we can spin it. The other thing you could do if you didn't want to just spin it is you could just move the magnet closer and further, just move it in and out. If you've ever had one of those shake flashlights where you shake the flashlight up, so it'll be like a flashlight like this, here's the flashlight part, and then inside the body of it like this, what it has is this coil of wires in there like that, and then there's this magnet inside there, and you shake it and the magnet goes up and down through the coil, and it actually generates power, charges up a little storage thing, usually like a little capacitor or maybe something like that, and then that is used to light a light bulb and you get light. And so mostly this kind of changing of flux is used to generate power. This is also ultimately what they do in power plants. They spin a giant magnet near a coil of wires and it produces electricity. That's how the alternator in your car works. That's how all these things work. They generate power through this change in flux. Okay. Another way we can do this, so this is moving a magnet near a coil. So that's like maybe way number one. Way number two, okay, this was number one. Way number two would be to move the loop. So we could have a big magnetic field, say pointed into the screen here, right? And pointed into the screen like that. And we could take a loop like this and move it into or move it out of that magnetic field. Push it in or pull it out. When it's out here, there's no flux. You put it in there, and then suddenly, right, here's the loop inside there. Now it's got flux through it. There's a magnetic field pointing through it. It's perpendicular to it, and that's creating a change in flux. Now, when you do this, you have to think about this. You have a bunch of little charges all along this edge, right? So let's say you have a bunch of little charges, little electrons and protons and everything in here. So as you shove this into it, there's going to be a force that acts on this. It's going to act on this change in flux, and you can actually make it difficult to push this in or out of the magnetic field. And this is used. It's called for magnetic braking, right? So you can use this to slow things down. It can cause, especially if this is not an actual loop, if this is like a full piece of metal, it can cause what are called little eddy currents inside it, and these eddy currents just make this thing want to stop. They end up trying to stop this thing, and so you can get magnetic braking with this, something like what they would use on roller coasters or something like that to bring the roller coaster to a stop. They have it run through a really strong magnet, and it ends up breaking it. The third thing you could do is similar to the second thing, is just, here's our magnetic field again. But this time, we're going to leave our loop in there. I'm going to make this loop here. And what we're going to do is say, here's our loop. I know I'm drawing just square loops, but it doesn't matter. And what we're going to do is along this axis here, we're going to spin the loop. We're going to spin it. So at this moment, the field is parallel to the surface, so it's pointed through it, remember, parallel to that vector that's perpendicular to the surface. But as you spin it, so like let's say we waited a moment later, it'll be like that, right? It'll turn on its edge, and when that happens, right, this is like picture number 2, when that happens, all the flux is going down the sides of it, and so here there's no flux, and here there's a lot of flux. And then as this continues to spin and rotate, it basically is parallel to the flux, and then it's not parallel to the flux, then it's parallel to the flux, and it's not parallel to the flux. So the flux will keep going, right? So like this was picture number 2. It'll go back and forth between these things, right? And it's going from basically zero flux to maximum flux, to zero flux to maximum flux, zero flux to maximum flux. And that's a way we can change the flux like that. Another way you can do this, right? Oh, and this is kind of the beginnings of an electric motor, because it would cause a force on this loop, and we can get this loop to spin. If we want to run electricity through this loop, it can make its own flux, and we can get this thing to spin. And so it's kind of like the first little beginnings of an electric motor. There's more to it than just the flux, but we can talk about that some other time. A fourth way would be change the area. So change the area. You can imagine, if I just use this same picture again, if I took this loop and I suddenly grabbed it and stretched it out and expanded it so it was bigger, well, then it'd have more flux going through it. Same magnetic field and everything like that, but we'd have more flux by change the area. This is actually used in medical devices. What they can do is put a loop of wires around you, like in a belt, that goes around your chest, and as you breathe and your chest expands, you're going to expand that coil of wires, and then as you exhale and your chest, your chest decreases in size, it's going to contract that coil of wires, and then they can just use the magnetic field from Earth and just constantly measure the flux, and they know that you're breathing if the flux keeps changing. All right, because you're breathing, you're going to constantly keep changing the size of it. So changing the area. Oh, another one this right here works for is detecting when you're at a street light. They'll put those little, you see those little rectangles cut out in front of stop lights. Inside that is a giant coil of wires, and when you drive your car over it, what it does is it magnetizes. It's got a very weak electric current running through it and a little very weak magnetic field. But when you drive your car over top of it, what it does is it magnetizes the engine block in your car, which is a big hunk of iron, and that magnetic field that gets created in the engine block adds to the magnetic field that's going through here and increases the flux. And then it can detect, basically by increasing the field strength. That would be the next way that I was going to talk about. You can increase the field strength by doing something like that, and then suddenly you've detected when the car is sitting there because the flux went up by a little amount. So that's kind of, I guess I should say, 3/5 now on that picture. And then And then that's pretty much it. So these are our main ways to change flux, right? Moving a loop, changing the magnetic field, or you can combine them all. You can change the magnetic field while changing the loop size and all kinds of stuff. Put it all together, they all cause a change in flux. And so what happens is this change in flux, what we have is Faraday's law, okay? So like if I look at this and I say, okay, uh, I shoved this into the magnetic field and I added flux to it, okay? And this is how you have to think about these things. So I started with no flux and now I suddenly added flux. And what this guy does, what this loop says is, no, 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 I don't like that flux. I want to cancel it out. And since the flux is pointed into the screen, it tries to create flux pointed out of the screen. It tries like that. And so what current would create a magnetic field pointed out of the screen like that? Well, you use your right hand rule. You wrap your fingers, or actually you do it backwards this time. Your thumb points out the direction of north, so the direction the magnetic field is pointed, and then your fingers are going to wrap in the direction of the current. So if you shove this into the magnetic field, you would get, in this situation, a counterclockwise current. Okay? But now let's do it the other way. So now let's say we have it sitting in our field. So let's draw our field again, right? Here's our field. And we have this wire stuck in our magnetic field, and it's got flux into the screen here. And now I take and I move it out of the field. Well, now it's lost. So here we gained, and it gained into the screen, so it tried to cancel it out by creating current to cancel it out. Now here, it's losing the flux. It had flux pointed in through it, and now it lost it, and so it wants to try and gain it back. So it tries to create a flux. It tries to create a current that will add that flux back in. So you do the right hand rule in reverse, point your thumb in the direction of the field, so your thumb into the screen, and your fingers are going to wrap clockwise. So that would create a clockwise current. Okay? And so if I were to keep continuously pushing and pulling this in and out, when I push it into the field, I get a counterclockwise current. When I pull it out, I get a clockwise current. So back and forth, clockwise, counterclockwise. And the same thing up here. When I add the flux in this way, it tries to create current in a direction that makes flux in the other way. When this spins around and adds flux in this other way to the right, it tries to create current in the opposite direction to create a flux in the other way to cancel it out. It tries to undo whatever you do. And so as you change it like this, what you get is you get current running one way and then the other, and one way and the other. And that's part of this power generation. It makes alternating current. And the same thing here. As this goes down, it creates, as it's going in, it creates one field. As it goes out, it creates the other, and it will create an alternating current too, which we learned about, or we will learn about when we do circuits, and it's which you should have by this point. And you get that alternating current. And so this is how alternating current is made. It's by changing the flux in such a way that it makes current go back and forth. It keeps flip-flopping, trying to undo whatever you're doing to it. Okay? You add field, it tries to create a current that cancels it out. You take field away, it tries to create a current to add it back in. All right, that's the real important thing. So next we need, that's basically Lenz's law. What we've got now is, well, how much current does it make? And we don't really ask how much current we make, we ask how much voltage does it make, because how much current gets made depends on the resistance of the surface. Is it really conductive or is it just a little bit conductive? So what we worry about is how much voltage does it make. And so this is from Faraday's law of electromagnetic induction. So we're finally to the induction where we're creating this current, and this is called this is the voltage that's produced. Remember, we talked about this before. Voltages that are supplied to a circuit, the thing that gives us power, is not just called a voltage, it's called an EMF, right? The electromotive force, the really the unfortunate name because it's not a force, but it's still called that, and we did it with this epsilon. And so this would be what would provide us our voltage. So this is our EMF, our voltage, supplied voltage, and it is equal to negative, because it tries to do the opposite. Remember, that's our Lenz's law. It hates the change in flux. And for something instantaneous, a derivative of flux with respect to time. For the non-calculus, we can approximate this by negative change in flux per time. So this is essentially the EMF is the rate of change of flux. It's the rate of change of flux. Okay? And so this is the EMF that's created just for one single loop, but in your book, what you're going to get in your data booklet, you're going to get it with that whole flux linkage thing, which is just the whole bunch of terms, the extra area, its number of turns, not terms, that, change in flux per time, and that's the equation that you're going to have to know. Okay? So that's the equation you need to know for the voltage produced through changing flux. Now we can take this and do one more thing with it. We can get one more voltage with it with a situation that's kind of a change in area, and it's more like it's a sweeping out of an area. And so what we're going to do in this one, and this is an important situation that you kind of have to know and understand pretty well, and this can lead us to generating power pretty easy. But what we're going to do is put a bar, not a loop, but a bar, a metal bar or something like that, a conductive bar in a magnetic field, and we're going to move it really quickly so that it ends up, in some new position over here. Okay? And what we want to do is, if we look at this, this is sweeping out an area here, right? This area is swept out by this. So this area is going to have a flux. And if we look at this bar and we say this bar has a length L, okay, and it's moving at velocity V, we're going to call that the velocity, then what we can do is we can look at this and say, all right, well, our voltage is our change in flux, negative change in flux over change in time, and that's negative B delta A, because we're not changing the magnetic field, we're changing the area, right? From zero area to an area it's covering, delta T. And if you think about delta A, well, what is this area? Well, it's this distance here, this distance times this height, D times D, or D times L, sorry. So area is D times L. But what's D? Well, D is velocity times time, right? So this is velocity times the amount of time it took times L. And that's our area. So we can rewrite this as negative B V delta T times L over delta T. And the delta T's will cancel, and you're going to get that you get this, the EMF is negative B V L. And this is a very specific situation right here where we have a bar moving through a field like that. And it works like that. And the other way you might see this then is, of course, with the flux linkage. If you had like multiple loops and stuff of this, you had, or not multiple loops, multiple bars. So like, say I took and made a bunch of bars connected in parallel like this, right? And then I shoved it through a magnetic field, right? A magnetic field like that. Then it would be the number of these bars, 1, 2, 3, 4, 5, 6. I drew 6 of them there, right? And they'd all 6 be creating this this EMF. And so however many of them are, we can change this to negative N B V L. Okay? That, I think, is just about everything for this video. Go back, watch it again, spend some time thinking about it, and hopefully it'll start to make sense.